Hello and welcome to this video on the symmetry of inverse functions graphs. We'll begin by reviewing a property of inverse functions that we saw previously and then use that to investigate the symmetry of inverse function graphs. So we are going to let f be a function that takes inputs from set A and pairs them with outputs from set B, such that f has an inverse function that we'll call f inverse. And then if y equals f of t, then we can express the exact same relationship from a different perspective by writing t equals f inverse of y. And that tells us that if y equals f of t, then we know that t was the input and y is the output. So the point ty lies on the graph of f. And subsequently, if t equals f inverse of y, then y is the input for the inverse and t is the output. So the point yt lies on the graph of f inverse. So let's go ahead and apply that to a function. We're going to let q of x equal x plus 1 squared minus 2 for all x greater than or equal to negative 1. So a couple of things to point out here. We know that this is a quadratic in vertex form. So we know that this has a vertex at negative 1, negative 2. And just looking at that, we see that it does not pass the horizontal line test, which means q would not have an inverse function if we looked at the entire parabola. But because we are restricting the domain so that x is greater than or equal to negative 1, we're only looking at the right half of this graph, and just the right half of the graph that I highlighted in purple does pass the horizontal line test. So function q does indeed have an inverse function. So take a few minutes and try to answer these 3 questions on your own. All right, let's see how you did. So to begin, determine and graph at least 3 points on the graph of q of x. Well, we already know q of negative 1 equals negative 2 because the vertex is at negative 1, negative 2. We could evaluate q of 0 and we would get negative 1. So 0, negative 1 is on the graph of q. q of 1 equals 2. So 1, 2 is on the graph of q. And then we'll just do one more. Q of 2 equals 7. So we know 2, 7 is also on the graph of q. So I'll plot those. Here we have negative 1, negative 2, 0, negative 1, 1, 2, and 2, 7. So using what we know about inverse functions, we can determine and graph at least 3 points that are on the graph of q inverse. So for example, because q of negative 1 equals negative 2, we know that q inverse of negative 2 is going to equal negative 1. The input and the output reversed. So negative 2, negative 1 is on the graph of q inverse. Similarly, because q of 0 equals negative 1, q inverse of negative 1 equals 0. So negative 1, 0 is on the graph of q inverse. Q of 1 equals 2, so q inverse of 2 equals 1. So 2, 1 is on the graph of q inverse. And lastly, we can say that q inverse of 7 equals 2. So 7, 2 is on the graph of q inverse. So we'll go ahead and plot these points. Negative 2, negative 1, negative 1, 0, 2, 1, and then 7, 2. Try to sketch a nice curve here. Okay. And so we're looking for a pattern here, some type of relationship between the graph of q and q inverse. And to help you see that pattern, I'm actually going to graph this line, y equals x. And one thing you might notice is that For example, -1, -2, and -2, -1 are symmetric over that line y equals x. They're reflections of each other over the line y equals x. And that turns out to be true for all of the corresponding points that were on Q and Q inverse. They are all reflections over the line y equals x, which means that Q and Q inverse are symmetric over the line y equals x. So I won't write that here. I'll just point it out in our last slide where we'll summarize what we've seen. So because if y equals f of t, then it follows at the point ty lies on the graph of f, and if t equals f inverse of y, then the point yt lies on the graph of f inverse. So ultimately, because the inputs and the outputs are being reversed, what we can say is that the graphs of f and f inverse are reflections of one another across the line y equals t.